Good afternoon. I first would like to thank the Linux Foundation Energy to give me the opportunity to speak today. I'm Nicolas Omont, the Vice President of Operations of Artelys. And I will speak about Continental-Wide coordination of the power grid with PowSyBl, and especially PowSyBl open load flow, the main load flow of PowSyBl. First, I will just tell a few words about Artelys, because you know most of the TSOs or DSOs that have been speaking here, but you may not have heard about Artelys yet. So we are a company specialized in mathematical optimization tool, operations research. And so we have recognized expertise to lead scientific consulting and projects. We've got a large experience in the power and gas sector, in the energy in general, and also in transportation and supply chain. And so we provide both software solutions, either tailor-made or off-the-shelf, or consultancy services, where we rely on our quantitative analytics skills, especially in the energy sector. So we are 20 years old. We have grown sustainably since. We are about 100 people now, with our main offices in Paris, and with an office, 2 other offices in France. We have opened subsidiaries in Spain, in Belgium, and also one in Canada. And we dedicate around one quarter of our activities to R&D. As I expected that the room would not be familiar with power grids, I prepared an introduction about power grid security analysis, just to make sure everybody understands. So the overall talk will not be very technical. I try to focus on organizational aspects also of open source projects, but I think it's interesting to understand what we speak about. So this is a power grid between a portion of the power grid. You may recognize France and Spain, and the lines between France and Spain. So what happens with the power grid is that when you have an outage, the electricity flows goes automatically and instantaneously through the remaining path. So here you see there are 4 paths between France and Spain, 4 set of lines. And if, let's say that initially there is a large export from France to Spain, that you can see with the arrows on each of these paths, these corridors. And then let's say that there is a lightning or something, so that the corridor in the middle is out of service. So in this case, automatically the flow will be redistributed on the 2 remaining paths, and so there will be an increase of the flow on these lines. So that's tricky, and that's not usual. If you take a telecom network, it does not work like that. If you lose a link, well, it's not going to overload the other links. There will be saturations, but somehow the flow rate will be reduced, and everybody will see something. But somehow it will be handled automatically. Here, the fact that the physics is such that the flow will go on the 2 other paths is good in one way, but in the other way, you have to make sure that the overload, the additional load does not create overload on the other path, because if it's the case, then these other lines will also trip, and then you will have a cascade. That is, let's say that this flow is too big for this the path here. Then the line will open, and everything will go on the last one, and that for sure will open, and then you will have separated France from Spain, and you are at risk of a blackout. In this case, more probably in Spain than in France, but it could also be in France. It's just that if you lose the connection between France and Spain, here, given that France is exporting to Spain, then it's Spain that will have difficulty to match the demand with additional generation. Whereas in France, or in the remaining part of Europe, it's usually easier to find generation to stop very quickly than to find generation to start very quickly. That means that you need to do a lot of power grid simulations for all time horizons. So at the TSO control room, every day, every hour, all the time, there are computers that are trying to anticipate the grid behavior on the following day, so making a forecast of the grid states. And then for each of the grid states, it tries all the contingencies. So for example, right now, there's likely to be a computation that looks like what is going to happen if tomorrow at 2 o'clock this line is lost, making sure that it does not create overload on the other lines. So that's what we are going to speak about. So for the vocabulary, a line outage is called a contingency. Well, a contingency can be something other than the line outage, but if you don't know more, it's enough to understand that a contingency is losing one line. The assessed elements are the remaining lines. So after a contingency, you look at the flow on some lines, not everything. I mean, if you lose a line here, probably useless to look at the flow at the bottom here. So you're going to look at the flow on some neighboring lines. And curative remedial actions, it's a bit tricky, but somehow at the control room, if such a contingency occurs, they can do things. They have maybe five minutes to do something, and that's what is called curative remedial actions. Maybe there is an overload, but in 5 minutes the dispatchers can do something to mitigate it. So in this case, the simulation is going to say, okay, there's no problem. Even if there is an initial overload, we're still in a safe state, because if it happens, the dispatchers know what to do. So this is on one boundary. And then the project we are participating in is at the European level. Indeed, individual transmission system operators are responsible to operate safely their own grid, but the grids are deeply interconnected. Therefore, coordination is needed. It has always been needed for the last 60 years, but it's more and more true, and especially for cross-border flows between countries. That's why regional coordination centers like Coreso and TSCnet have been created to coordinate the operations within each region. So in Europe, the security is coordinated per region. Regions are a set of boundaries. So a given country can belong to many regions. And we have a main region that is the core region in the middle of Europe, from France to Poland. Here it's really meshed, and you cannot, the security needs to be coordinated at this level. If you try to split this region into independent regions, it does not work. And then there are other regions like southwestern Europe, the Baltic region, and of course on the other side, UK and Ireland are alone. And there is another region in the southeast of Europe. So Artelys is participating to the CORNET program, which covers 25 TSOs from 2 regional security centers, Coreso and TSCnet. And overall, they cover all the area, potentially all the area in blue and in yellow. So it's most of Europe, and it covers five regions. And so we are providing at Artelys the grid-related computation modules, and we are doing that using PowSyBl. And we have a partner, which is a Czech company called Unicorn, that is providing the platform. And so the tool that the dispatchers will see is from Unicorn, and then it will delegate the computation to the modules we are building based on PowSyBl. So then let's dig into what is a security analysis more in detail. So for a TSO, what does it look like? As I told you, the first thing is that you have to usually you forecast the future grid state. So what will look like the flow on the grid for tomorrow. And to do that, you need to know generation schedules. You need to have consumption forecasts. and you need to have exchange schedules with neighbor TSOs. And so you need that for your own area, the TSO, and then for your neighbors. And the further the TSOs are from you, the less information you need for them. And with that, you're going to be able to compute a grid model that is representative of the time horizon you want to forecast. And then the computation will somehow simply consist in listing contingencies, assessed elements, and remedial actions. So all the lines you want to check that is going to be safe to lose them, and then all the assessed elements you have to look at after each failure, and all the remedial actions you want to apply after each failure. And you compute this security analysis, and hopefully what you want is that, okay, every contingency is safe, there will be no overload, whatever happens. Or, no, it's not okay, what we forecast, what is forecasted is not safe, and you have to do something. So, for example, it could say, on the contingency, which is the loss of a line between France and Spain, Argia and Hernani, then it's not okay because after the contingency, you have the flow is too large, maybe 150% of the limit on Argia Calais. Then a simple curative action, it's not real, I just invented it, could be to disconnect the line. So it happens. It's quite funny to see that when you have a problem on the power grid, if you have an overflow on a line, maybe just removing the line may solve the issue. It's just, when you think about it, it shows that it's not normal. You remove something, it works better, but it's like that. And then maybe it's still not okay because once you have done that, you have solved this violation, but you still have another one on another line. So the dispatchers have to find a solution for that, and there are many ways to do it. And that's how it has been working for decades. So before, it was okay to do like that, but as I told you, we have increased flows between TSOs, and so the amount of information that TSOs need to exchange to coordinate themselves is way larger now. Before, mainly France and Spain, the French TSO and the Spanish TSO will discuss together and solve the issue on the French-Spanish boundary. And somehow, maybe it's still working, but now they have to work with the Portuguese TSO. But in the core region, in the middle, between France, Poland, Germany, all these countries, it's impossible now to coordinate bilaterally. A contingency in one TSO can create problems for many of them, and then can be solved by remedial actions that involve many other TSOs. So the coordination really needs to be centralized by region and cannot continue to be done by each TSO and with bilateral problem solving. That's why the regional coordination center have to make two kind of operations. The first one is to do a pan-European merging in order to obtain a single common grid. I will explain that later. And so they can have we can have a single vision of what will be the European grid tomorrow at 2 o'clock, for example, and then perform a single coordinated security analysis for each region, knowing that the core region is the largest one. So, of course, this security analysis will focus on cross-border flows, and I don't know, but for flows in the electric peninsula in France, for example, there's the region of Brittany, which is on the western part of France. It's not of European interest to understand the security analysis there. It does not need much coordination. It can be performed by the French TSO alone. So the coordinated security analysis focuses on what's important at the European level. So what does it look like? It's a bit more complex than before, because now you've got each TSO that sends an individual grid model, and then there is a first module that does the merging and also the scaling of the individual grid models. There is a quite complex computation here. It's not just putting all the files together, because somehow it's needed to adjust the net export position of each country given an auxiliary file. And so this file says how much each country is going to export for each hour of the next day. and it needs to be used to adjust the individual files that may not reflect these positions. So we are providing a module that performs that. It can be quite tricky because you see sometimes we have partial merges to make, and in this case I just put the picture because when I saw it I said, oh, I would have never thought about that before I see that. It's quite complex because the merging is partial and it separates the countries for which we don't have the IGMs in two independent parts, which create quite a few complexities. And then once we have the common grid model, somehow we do as before. We take assessed element, contingencies, remedial action, and we compute a list of issues. And then the TSOs have to solve the issues. So we send back the result to all TSOs. And also the common grid model is sent to the TSOs because they can be used for local security analysis. So on the performance needs, so the process I described here is for the next day and then for within the day. So for example, if we do for the next day, we usually have 1 timestamp per hour, 24 timestamps. We can have several thousands of contingencies, maybe 2,000 or 3,000 easily. We need around 1 second to compute each contingency. And the requirement is to perform the computation in less than 5 minutes. So you can see easily that we will not be able to do that on a single computer, even a large one. That's why in PowSyBl, we have a module that performs the distribution over our HPC cluster using Slurm. So this is the basic architecture. There is on a Kubernetes cluster, we have a microservice that receives the demands of the request for security analysis, and then that transfers the demand on the HPC cluster. The job is performed, and the results are gathered thanks to an exchange, thanks to a shared data storage. I think the most interesting part of this is the open source development organization that we have to do that. So, PowSyBl, as you know, is a project with governance is made by the Linux Foundation Energy. And there are many sub-projects. So here I don't speak about PowSyBl in general, but mainly about Open Load Flow sub-projects and a few other for the HPC clusters. So what's interesting is that both Artelys for the Cornet project and RT are contributing to it. So RT is doing it for its security analysis at the French level, at the TSO level. And Artelys is doing it for Cornet for the European Coordinated Security Analysis. And so it's beneficial to both because, of course, we would have to do twice the development if we didn't share it in this way. And so the organization is quite smooth, and we can work as if we were a single team in a single company, thanks to this setting. RT on its side has private repositories for the things that are not shared, because not all the needs are common. With the developers are RT employees and contractors. On Cornet side, the Coordinated Security Analysis project also has private repositories, especially for the interface with the platform. It's specific to this platform from Cornet and provided by Unicorn, so there is no need to make it open source. And the developers are from Unicorn for the platform and Artelys. And overall, we managed to work together with the framework provided by the Linux Foundation Energy, with the technical steering committee, and then we have regular meetings of developers. The only point where it can be tricky is the data exchange, because as you may know, the grid data is very confidential. So that's something we cannot exchange between this part of the project. We both make sure we exchange information on load flow cases that don't work, for example, but we cannot share the grid data in itself. I would say it's not a limitation of open source, but more a limitation that the data, even if the code is open source, the data corresponding is not. Despite this small limitation, I would say it works quite well, and it's been going like that for nearly 8 months, I think, and it's quite beneficial. As you may see, every 2 months there is a new release of Open Load Flow, and we have many new features, and most of them are useful for both projects. Even if the project is not finished, I have a few takeaways that I have a few intermediate conclusions. For me, open source projects are a great opportunity to make organizations work together without needed full strategic alignment. PowSyBl is very modular, and so the mechanism that I have shown, where there are private repositories, public repositories, is made possible indeed to work with a modular open source structure in which we share only part of the needs and part of the objectives. Overall, if you look at PowSyBl and GridSuite, it's based on microservices. So for each microservice, you can decide whether you have the same need or not. If you look at the internal format, it's extensible. So of course, maybe there are some devices that are specific to RT network that are not in the CGMES format. So with extensions, it's manageable. On our side, it's going to be the same thing. We are going to develop some devices, the models of devices that are not in the CGMES. So we will have to make others that are not exactly the same as RT. So thanks to a very modular framework, we managed to have a common base, and then to be able to customize it for the needs of each project without forking, because of course it would be the worst that could happen, is that we have to fork a module, because in this case we will not benefit from the common development that decrease the cost and increase the speed of the project. So if you start such a project, of course you have to make sure that functional needs are sufficiently aligned, and here it's the case. I mean, a security analysis look like the same at the TSO level and at the European level, but no need of 100% alignment. You need to have good interfaces between the public and the private parts, because this is where you will have to agree. And so the modularity should be, you should have more granularity than you need, and then try to anticipate as much as possible these separations. And also think that the interfaces will need to be designed deep into the functionalities, so that you need hooks or triggers that let you call the right function at the right place quite deep in the code to manage the different needs without having to fork. But with that respect, PowSyBl was made with that in mind, and it works quite well. There are a lot of ways to customize it, to adjust 10 or 15% of your needs that are not standard without needing to fork everything. And then, of course, on the project side, you need that the project plannings are sufficiently aligned. If it's not the case, it's likely that the one who is in a hurry will have to bear the largest share of the development, and this is not what you want. You want to share the development burden between the partners. Here I think the governance of the Linux Foundation is very good. It helps to give visibility to the others of what you intend to do in the next 3 to 6 months. So with this TSC meeting every month, it can trigger some useful discussion on this perimeter. And then also another important part to agree on the perimeter extension. So keep it as small as possible. I mean, if there is no collaboration need on some part of the software, just keep it on your side. I mean, sharing makes sense only if you think that you're not going to be alone to develop. Else, maybe you want to do it to show to the other that it's open, but somehow being more than one to decide for something is always there's a little overcost. So think well, make good interfaces to keep the common part to the necessary part only. Okay, I kept my presentation quite short. Somehow it's more longer than I expected, but quite short. So we have time for questions now or later. If you have technical questions about what does the load flow, whether we support CGMES 3.0 or that kind of thing, you can ask them. If I have the answer, I'll give them. If not, I will find them. Yeah.
On a broad level, what do you see as the most important differences between also how do you pronounce it? PowSyBl?
It's the same way, PowSyBl. Yeah, I think we say it. It was.
What are some key differences between PowSyBl and some of the other open source power system models?
Yeah.
Like PipeSwap,
Yeah.
Power, NAP, Power.
Yeah. So I think that so functionally it does basically the same. I mean, a load flow is a load flow. Security analysis is security analysis. However, here the focus here is to make an industrial tool that will run 24/7 reliably. So that's why the basic choice was to have as much as possible in Java, not in Python, not in another language, because we know that the platforms are always in Java. So it means that we need to integrate fully. We need to have the same CI/CD platform. We need to be able to use the same processes to show the quality of the code. And so being in Java is really a big plus. And so starting from that, the focus is really on being industrial and reliable. So the SIM CGMES import is really really to the standard, to the best standard, and we want to be able to cover everything that's needed by the European TSO. We are not going to say, okay, we managed to read it, but somehow your non-linear shunt with your reactive remote control. No, we don't handle it. So we try really to cover everything that's going to be needed for all this to work. And yeah, I mean, it's not a study tool, it's not a research tool, it's really an industrial one. So then, given that there is also demand of, because as people trust it to work, then they say, okay, but I know only Python, and I cannot use it, it's Java, and it's true, it's more costly to start with, because most of power engineers know only Python. So that's why in the last year, PowSyBl has been developed, which is a package that allows to use all these powerful tools, but directly from Python. But somehow that was a second step. It works well, it's quite efficient, and it relies on a quite complex but efficient bridge between Java and C++ and Python. And thanks to it, it's also usable instead of Panda, especially if you want to have something that have industrial quality. For this industrial quality, I also think about security standard. So right now, PowSyBl has already a best practice badge from the Linux Foundation Energy that we are going to go to the silver level. I hope quite soon, and that's very important when you want to deploy operationally for critical systems. Yeah.
I have a question. The last slide you presented, the key takeaways, the last why is this particularly in this project a key takeaway? And of course, you are a commercial company. Could you give an example how you solve this?
So in this project, for example, we did a gateway that converts the internal platform format to the possible IIDM format. So typically, we did not open source this gateway because it will be useless to open source an interface to a proprietary format. That's the kind of thing I want to say. I don't want to speak instead of RT, but RT also had many private repositories to model devices that they have on their grid that are not used anywhere in this way in Europe. So, and then sharing this with the open source community wouldn't make no sense. Then the fact that I'm a commercial company is not very important in this case. I'm a service provider to Cornet. So if it was proprietary software, it would have been software belonging to the Cornet project, not to my company. But in this case, we said to Cornet, that's going to be cheaper if you put it open source, because we are going to share the development burden with other partners of the community, especially RT. So for me, as a service provider, it's a bonus if I can manage to show that there is a strong community behind the software, because I know I will be able to bid at a lower price and get it compared to proprietary software. Okay, I've seen the 1 minute paper, so I suppose it's time that I stop anyway. So thank you very much. I don't know, I think.
In the roadmap, the ambition to have a -30, so system like -30 distribution.
You mean the theme for the